Yeah, hi, I'm Mahesh Paolini-Subramanya. I head up software development at a company called Ubiquity Networks. Standard question, how many of you have heard of us? Wow. Okay, so we are the largest network hardware provider that you have never heard of, most of you, that is. We provide network hardware to interconnect any two places that you can't pull a cable in between. We're worldwide. We're huge. We sell like millions of things a month. We make things. It's amazing. We actually make things you can hold in your hand, and we make things that pass what we call the break test. You know, you hit somebody with it, and the person breaks, not the thing. Which, try hitting somebody with a Linksys router, see what happens. Anyhow, by the way, things like microwave cannons to enterprise Wi-Fi to all sorts of fun stuff. Good hardware, buy some. It's good for you. It's good for me. Anyhow, so this is actually a bit of a perfect segue from what Garrett was talking about. I'm going to be going through essentially the philosophy or the Buddha nature of Erlang, what the point behind Erlang is. This is a talk about Erlang, but it's not really a talk about Erlang. It's a talk about fault tolerance and reliability and what it actually means to be a fault-tolerant, reliable system. And the thing is, in life, the one thing you can be certain about is, you know, weird stuff's going to happen. Things that you expect are not going to happen. Most of you in software have invariably dealt with something along these lines. Something crashed, bad stuff happened. If you do any kind of service where other people depend upon you, you usually get one of these things. And it's like, oh my God, what happened? Fix it, fix it. And oh my God, this thing came off. Fix it, exactly. And that crashed too. Is that working? Not? Yes? Excellent. Okay. Okay, so you get the horrible phone calls from people saying, fix it, what's going on? And then after you fixed it, immediately your boss or your customers or whoever go, come on, why didn't you test this stuff? Why did it crash? And the thing is, you probably did test it. In fact, you tested 7 ways to Sunday. The thing is, what you can't prepare for is the absolute unexpected. You tested for the 100-year flood. You got the 1,000-year flood. You tested for, oh, what happens if an asteroid hits Equinix East? Well, what if an asteroid hits Equinix East and Equinix West? Right? You know, something bad is going to happen. And that, in the end, is the realm of fault tolerance. And the point behind fault tolerance, the real thing about fault tolerance is we all think we know what it means to be fault tolerant or reliable and so on. And we probably have a pretty good idea in some of our cases. But the reality is there is a bit of a formal definition of fault tolerance. Like an actual thing that says this is what a fault-tolerant system is and this is what it must do. And when you get down to it, fault tolerance consists of 6 things. And basically 6 things. If you can fit these 6, you're done, you're set. Thing number 1, concurrency. You need to be able to do more than one thing at any given point in time. Why? I mean, pretty obvious. If you can only do one thing at a time, and that one thing hangs, you're dead. You need something else to go, hey, that thing hung, and fix it. You need to be able to know that that thing hung. Fault detection. Fault identification. You need to know not just what happened, but why it happened, or the symptoms. When something bad happens, you need to be able to isolate it. You can't have it spread. It's what the CDC exists for. You got the flu, don't travel. Stuff like that. Once you isolated it, fix it. Code upgrade. This one's a tricky one. This one is a tricky one. It just crashed. Woo. Let's see if... Remember I said if you can get 3 things working, life will be good? That's a 3rd one. Yep. Hello, Macintosh. I shall have to manually punch the button on this thing. Stable storage, the tricky one. Point behind stable storage is when something bad happens, think of it as save game. You need to be able to retreat to your previous saved status and then continue from there. It's the one that we never think about. It's a very important one. Keep that one in mind. So 6 items: concurrency, fault detection, fault identification, error encapsulation, code upgrade, stable storage. If you can do those 6 things, you got a fault-tolerant and reliable system, guaranteed. Let me rephrase that. If you do those things and they actually work, you have a fault-tolerant and reliable system. That's an important part too. So needless to say, Erlang kind of does this. But the point is, it isn't just that Erlang does it, it's baked into the system. Garrett went over a bunch of these things earlier on. I'll kind of take you through a couple of them, well, through the specific examples, in short, one by one. So let's start with concurrency. Won't go into the gory details of this, but concurrency is baked into the very genes of Erlang because of the whole process model. You got processes. Processes are parallel. Processes are independent. Processes require you to actually click on the button. You got asynchronous message passing. Essentially what that means is you don't have to wait for the other person to respond. You can't end up in a situation where everybody's deadlocked. Well, you can end up in a situation where you're deadlocked, but that's because you're a bad coder. It's not because the system makes it do that. There is no shared state. That's a very important thing. You can't end up in some kind of weird situation where you have no idea what's going on. Immutable data structures, another very important part. Just hold that thought in mind. We'll get back to why immutable data structures are important. But the thing is, when you put these pieces together in the Erlang process model, by definition, not only do you have concurrency, you have isolation, you have completely distinct standalone processes that work independent of each other. Brief aside, somebody asked a question about supervision earlier. In Erlang, all processes are identical. There is no special process. Supervisors are just processes like anything else. All processes are the same process. Well, not really, but they're exactly the same. It's just that some have special roles and some don't. You don't have super user processes. You don't have whatever. It's just the same thing. The point, there are a couple of things that provides, a couple of benefits that provides. One of the very important ones that is usually unstated is understandability. It may not be as efficient as you might want it to be, but you can completely understand and reason about the system, and that's a very important factor. The JVM, which is the one true virtual machine or whatever, as compared to the Beam, which is the Erlang's virtual machine. Beam's rock solid. I mean, you'll hit the heat death of the universe and the Beam is still running. JVM, oh, you can make it do that. It's just that there are 8 million switches and you have to get it tweaked just right for your particular situation for it to do what you need it to do. Understandability. It may not be the best thing in the world, but you totally know what it's doing and it works like a charm. Anyhow, moving on. Fault detection. Simple example of fault detection. Let's look at some code. Got a bunch of chores. One of the chores is feed the cat, and there are a bunch of different things you can feed the cat. You can feed oatmeal, soap, science diet, or pretty much anything else. And the thing is, each one of those has a very specific response. And as part of your chores, there's only one of these things that is a good thing. Everything else is at best not good, and at worst really quite bad. And for the non-Erlang readers, basically what that translates to is if you give the cat oatmeal, then you're going to get a response which is okay and purring, which is a good thing. Anything else is going to result in like catastrophe. So let's just say for argument's sake, you decide to feed the cat oatmeal. Boom, the very first thing that happens is the system craps out. Fault detection, instantaneously and immediately. Bad things happen. That's fault detection. It's simple. And you'll get an exception error, and the reason you got the exception is because error unhappy is not the same as okay status. Trivial, simple, easy. Fault detection. Fault identification. What happened? Well, we already saw that. You got the result, which was error unhappy. In the code, there's only one thing that results in error unhappy, which is when you feed the cat oatmeal. Your instructions to the cat sitter were not precise. The cat sitter was a dim bulb or whatever. He or she decided to feed the cat oatmeal because, I don't know, granola, something. Error encapsulation. Important point, you don't want this stuff to spread. So you fed the cat oatmeal. Cat's cheesed off, dog's pretty happy. It's a good point. It works. Which, to kind of take it through what Garrett was referring to, you got processes, we let processes crash. We don't care. In fact, you know what? We don't just let a process crash. What we actually do is let any and all set of cooperating processes crash. And this is another kind of relevant point that needs to be dug into a little bit. The point is, processes don't exist in isolation. I mean, well, they do exist in isolation, but things depend on each other. So when a particular process crashes, there may be a couple of other things in the system that depend on it for whatever purpose. Think about if your web server crashed, you need to clean up a bunch of database connections in the back end. Great, fine, go ahead and clean it up. All of those processes, let them all crash, let them all clean up, let them come back again. So those are the cooperating processes. And as we discussed earlier, supervisors can basically figure out what need to be restarted, and only restart them when necessary. Supervisor restarts your web server, which promptly crashes again, restarts it, promptly crashes again. There's something bad going on. It tried 5 times in a 10-second period. It didn't work. You know what? Crap out completely, raise a red flag. And your sysadmin gets a phone call. Actually, both of them are in here. That should be illegal, seriously. Exactly. Oh, on that note, Andrew, who's sitting back there, I remember way back, we were on a project together, we were flying down to Argentina, and I get a phone call from the chairman of the board saying, both of you can't be on the plane at the same time. It's like, come on, guys, our project isn't that big a deal. Who cares? Anyhow, code upgrade. Obvious, right? Give the cat cat food. Cat's happy. Problem is solved. The thing is, in Erlang, the actual code upgrade process is really simple and straightforward, which is maybe the single biggest untruth I shall state in this entire thing. But compared to other systems, this is ridiculously trivial. What you're basically doing is you tell your process, here's your old version. If you're running in this old version, take your old state, change to a new state, and run this piece of code to basically go from the old state to the new state. It upgrades itself. Life is good. It just works. There's actually way more complex ways of doing this for releases and stuff. But at the end of the day, it's actually something that is doable. It does not involve monkey patching. It does not involve the highly probabilistic effects of class loading, goofiness, whatever. It pretty much tends to just work. You know, it's one of those things that you don't even think about. We don't think about. It just works. Stable storage. Remember I said kind of really important that we don't talk about? The stupid, simple example, yeah, you know, you keep a bunch of extra cat food in the closet in case you run out, you don't have to try to give the cat oatmeal. The reality is, it means a whole bunch of different things, and there's an entire other talk involving what stable storage means, and that goes into the realm of persistence, polyglot persistence, how do you do distributed data stores across multiple systems, recover state, etc., etc. I won't go into it. We can talk about it some other day. But the point at hand is, at the end of the day, these 6 things, concurrency, fault detection, fault identification, error encapsulation, code upgrade, stable storage, 6. If you get these 6 things right, if you always think about these 6 things when you're coding, and you think about these as discrete, specific entities, you got a good start at building a fault-tolerant system. And it doesn't even have to be Erlang. I showed you some Erlang examples. It just works in whatever language you're using, whatever system you're using. In fact, let's take this one step further. Let's talk about systems. Apply this philosophy that Buddha nature of Erlang to systems. So let's go over it again. The same 6. Pick a couple of these. Concurrency, error encapsulation, and code upgrade. Right? That's loose coupling. You got multiple loose coupled components in your system. They can run at the same time, concurrency. If a particular component crashes, it shouldn't affect any of the other components. That's error encapsulation. If you've got good APIs and you're doing good service-oriented stuff, if you update one of the components, you don't need to worry about the other ones. That's code upgrade. It pretty much works. From a philosophical perspective, you're doing loose coupling, you breed trust, you get people, you can trust individual components because you can encapsulate those individual components, you know what's going on in them. You don't have to worry about specifically what's going on in there. And most importantly, and this is kind of the other way around, when I say you can trust them, I actually mean you don't have to trust them. All you have to trust is the inputs and the outputs work. You don't care about what's going on in the system. It's an important thing. Second point, you can devote brain power appropriately. Bit of a tricky point here, but the thing is, basically the more complex your system, the more you're worrying about interactions and less you're worrying about what the actual component is doing. So the more you can isolate and encapsulate your little individual component, the more you know what that one component does. The more you're certain about how it's going to behave. And the less you need to worry about its impact on other things. Yes, there are emergent behaviors and emergent properties. That's a problem for another day. If you get to the point where you have to start worrying about emergent behaviors, that's good. Seriously. Most people never even get to that stage. Trickier one, or a slightly different one. Loose coupling, you have fewer bugs. Well, eventually you have fewer bugs. So there's a little tiny thing about this one. Code. That's basically a slide that says, look, large amounts of code. There are a bunch of studies that have shown that it doesn't really matter how much or what language you're using, what system you're using, things along those lines. The number of bugs per 100 lines of code tends to be about 1.4. And yeah, that's a totally nebulous metric. What's a bug? What exactly do you mean? But it comes to about 1.4 bugs per 100 lines of code, which leads to a pretty straightforward thing. The fewer the lines of code, the fewer bugs you have in the system. Which, by the way, is a huge point about Erlang. The point behind this slide, incidentally, is the two things on the left are an old version of a system that we had developed, a PBX system we had developed. And, oh, see all those little things over there? That's AJA. One of the guys back there wrote most of that code. So anyhow, the point here is we went from Java, which is the two things on the left, to Erlang, which is the thing on the right. And our first complete write of the system, which was remarkably poorly written in retrospect, reduced the code base by a factor of 5. The second rewrite took it down by about 9.3 in actual numbers, by the way. Just straight compression. Doesn't really matter. You can reason about smaller amounts of code. Now, mind you, if you really want to go down that road, you could probably rewrite an APL and end up with one glyph, which you don't, but that's a separate story altogether. Anyhow, smaller, distinct components, less code in those components. The more you can reason about those components, the more you can eliminate bugs, hence, eventually fewer bugs in the code. A bit of a cynical point here. What about performance? Well, yeah, we can talk about performance of systems and so on and how it's not that important, or it's important, or Erlang is fast, or Erlang isn't fast. This isn't about Erlang. This is about how you design fault-tolerant systems. And the thing about performance Who cares? Seriously. I think Garrett asked this earlier, but it's worth asking again. How many of you have actually, I assume most of you have stuff in production or something involving production, right? Yes? Yes, okay. Turns out, by the way, these metrics are highly understated, but the bottom line is it turns out that around somewhere between 60 to 90% of every single project that gets initiated never actually makes it into production. The point behind that being, who cares whether your stuff is fast or not? It's not going to production. Screw it. Seriously. You've heard the whole thing, right? Make it work, make it elegant, then make it fast. There's a reason for that. Just get it working. That way, at least you have a fighting chance of getting it into production. Get it elegant. The reason behind elegance, there are a bunch of reasons, but the really big one, understandability. Elegance is essentially a code word for understandability. If you can understand it, you can reason about it, you can do stuff with it. If you ever need to get to the point where you need to do performance, oh, hey, go ahead, optimize it. Odds are you're never going to get to that state. Again, if you get to that point, good. You have a good problem to have. So anyhow, the point behind this is, don't worry about the performance thing. Loose coupling, yes, will be less performant than writing one single tightly coupled system. But you know what? If you write an assembler, you can probably get it blazing fast. Good luck. Systems, continuing. Fault detection and fault identification. When we're talking about the fault-tolerant systems. How to do detection and identification of stuff? Pretty obvious answer. Monitoring. We know this. I mean, yeah, monitoring. Of course you're going to monitor. A couple of things about monitoring, though, which are somewhat relevant. The obvious one, dashboards. Well, yeah, you got dashboards. You know what's going on. Everybody provides dashboards. It's all good. It's great. Two things that you absolutely should do that we kind of insist on, incidentally, but we've always insisted on. Thing number one, do out-of-band monitoring. Don't rely on your own system to do the monitoring. That's a recipe for disaster. You know that. But do that. That one most people do anyhow. That's a good thing. Especially nowadays, you can get third-party services to do the monitoring. Do those third-party services also run on AWS, which is what you're running on? A little bit more complicated. One step further, though. If you are writing your monitoring services, or you're writing component testing or integration testing or any of this stuff, what are you writing it in? We write our infrastructure in Erlang. All of our testing and system testing and monitoring services, okay, most of them are in Python. Not just because Python's, scripting, haha, nice. Also because Python is imperative. Erlang is functional. You have to think differently when you write your testing in an imperative language. When you're thinking differently, you will actually think of error conditions that you didn't think about in the first case. It forces you to kind of step back or to the side, look at the problem space again and figure out, how would I solve this in a different language, in a different thought process language? Same thing applies with monitoring. Don't just monitor it based upon what you are currently doing. Try to reason about it again from a different point of view. It's important. You'll be surprised how many error conditions and fail cases you'll find. A lot. Lastly, stable storage. Stable storage. This is one where essentially what we tend to do and what you should be doing is getting very long and very heavy on polyglot persistence. The point, just to make this really simple, the point behind polyglot persistence is use a data store or a data model stroke data store for your solution, for the component. Remember, loose coupling. For each component, use the solution that is correct for the job. And my point isn't SQL versus NoSQL. It could even be something like use Postgres here and MySQL there, whatever. Or Oracle, whatever. Seriously. But you could use something, but the point being, figure out what you need for that particular problem space, solve it based on the problem space. There are a couple of things that you'll find out when you do this. One is going back to the imperative versus functional when it comes to testing. That's a good thing. It helps you think about the problem domain in a very specific manner. The second one is it prevents you from crossing the streams. Crossing the streams is a bad thing. We know that. But the point, so why is crossing the streams a bad thing when we're talking about polyglot persistence? When you have this one single data store, we're going to put everything in MongoDB. Don't. But we're going to put everything in MongoDB. Fine. Okay, fine. We're going to put everything in MongoDB. You're now getting all your different components having some kind of impedance mismatch with the one place where it actually works. You know what? All I really want to do is store a bunch of time series data. Time series data in MongoDB is a bad idea. But you're doing it because, you know what? We have to use MongoDB. Corporate decision. Woo. It's horrible. But you do that. Or the other way around. We got Cassandra. We're going to use Cassandra for everything. So then you're writing this horrible CQL code that looks exactly like SQL, which is a really bad idea for those of you that don't do that, or have done this or not done it. Either way, it's horrible. And the next thing you know, you got this disaster of a Cassandra setup that now you're working with. So be aware of this. Be aware of impedance mismatches. Try and minimize those. What you'll find is your systems, if you go down this road, if you do these 6 things to repeat, and I know I'm flogging a dead horse here, concurrency, fault detection, fault identification, error encapsulation, code upgrade, stable storage. You do this, you design your systems around this. You'll find that they're automatically a lot more stable. You know what? Maybe they're not the most performant things in the world. Surprisingly, they probably will be performant because they're actually working. Big difference. I'll take a functioning system, which is not maybe the fastest one in the world. Well, anybody will take it over the one that doesn't work at all. So that's that. Let's take this one additional step forward. The same Buddha nature of Erlang, the same philosophy, the same thing about fault tolerance. Apply to organizations. When I say organizations, I don't necessarily mean your full-on company. It could just be your group of developers. It could be your little, just the 2 of you, whatever, just the way you work. Think about it from a people perspective. So the question is, what exactly do we mean by fault tolerance in this kind of arena? Well, it means different things for different people. Stupid example. People fall ill. Oh, if that person that fell ill, if that's Bob, and Bob is on the critical path for some project you're working on, you have a problem. That's not very fault tolerant, is it? You depended on Amazon for everything you do. This was the first time it went down, but it's been going down pretty regularly now, recently. Amazon East, at least. Regularly, as in once every 3 or 4 months. It happens. And the point isn't, ooh, Amazon bad. The point is it will happen. You can't rely on this kind of stuff. What's your CFO doing in Brazil? Seriously. The CFO wasn't supposed to be in Brazil. Why can't we get into the bank accounts? That would be a bad thing. Again, you know, what are your controls like? Anybody read Nicholas Taleb's book, The Black Swan? The more you squeeze risk out of a system, the more your tail risk increases. So bad stuff, the more risk you take out of the system, the worse the one bad thing is when it happens. I'll just leave it at that. But the point is, it doesn't matter how good you are, how well you've built your systems, something bad is going to happen. When that bad thing happens, how are you going to recover? And what are you doing to protect against that bad thing being truly evil? The key point behind the whole Black Swan philosophy, or protecting against a Black Swan, is, from an Erlang worldview, we don't try and squeeze risk out of the system. We accept it. We say, fine, it's going to crash. Great, let it crash. We'll deal with it. We don't want the tail risk to get to a point where it's horrible. Let's think about this from an organization perspective. The same 6 items, which I won't repeat again. But let's look at them one at a time. Concurrency. Micromanagement, right? If you are being micromanaged or you are micromanaging, that's a bad thing. If you are chaining, what's chaining? In a company, chaining is when there's a very well-defined workflow in the way things happen. For example, at our company, we are great. We're a tiny company. We're the best company in the world to work for. We are. Absolutely, we are. That's right. But no, seriously, we are. But the thing is, since we're also small, we've got basically one person in accounts receivable, one person in accounts payable. When the AP person goes on vacation, whoops, your expenses are on hold. That can be a problem. That's not concurrency. That's one single critical path on which things go down. It's okay for us because it's not that big a deal, but oh, it could be a big deal in certain other situations. I'll just leave it at that. Fault detection. So I already described this. Hey, Bill is ill. Supposing, just for argument's sake, Bill happens to work from home all the time. And is not very communicative. Do you know that Bill is ill? Bill happens to be on the critical path for this one project. How do you know that Bill's ill versus Bill's working on the project? The way you find out is when the deadline shows up and whoops, you missed it. And you lost the contract, or the thing didn't go up, or something exploded, or whatever. Fault identification. So yeah, you found out Bill is ill. That's not the point. You even know that Bill is on the critical path for that one particular project. That's not even the point. That's not the point either, because for you, that's not such a big deal. You're like, you know what? We're going to miss that component by 2 days, but that's fine. You know, we can make up for it in a week or so. That's easy for you to say. The team over there was relying on your component being there today because stuff had to go to fab today. If you miss the fab date today, the next opening at Foxconn is a month from now. Whoops, you just missed your Q1 earnings. Your stock just collapsed. That's not us, by the way. This is an example, seriously. Our stock is doing very well, thank you very much. But that's not the point. The point is, fault identification isn't just about knowing something happened, it's understanding the point behind what happened. What's the relevance to other people? And what you don't want to be in is in the situation where when something bad happens, you roll out the executive fire truck. Anybody know what the executive fire truck is? No? The executive fire truck is when something bad happens and the exec, whoever the exec is, me, says, step back, I'll fix this. Which just makes matters worse, but that's the point. But what happens is when you find out Bill is ill and this happens, the executive fire truck comes out and all hell breaks loose. Because then everything comes to a halt and you got to fix this one problem. Meanwhile, the other things are piling up somewhere else and you miss your Q2 earnings. You know, disaster. Error encapsulation. This one's an easy one. We already went over this. Don't let Bill be the problem. So Bill's ill. Okay, fine. Bill will get better, right? Bill gets hit by a bus. That's not a good thing. Well, for Bill, it's certainly not a good thing. But for you, it's really bad because, hey, guess what? Nobody else knows how that stuff works. Bill decided to write the whole thing in APL. What are these things? Seriously, anybody used APL here? Two people. 2 APL users. It's a spectacular language. It's like in the order of languages, you got C++, Java, whatever. Then you got Erlang, Haskell, etc., etc. Then you got APL, JKQ, all that stuff way over there. It's yet another level of insanity. It's good stuff, but weird. But Bill wrote it all in APL. Now you have to figure out how that stuff works. By the way, if you end up in a situation where Bill wrote an APL, just rewrite it. It's going to be faster. Not because APL's bad, it's because it's going to take you like 6 months to figure out what he did. And then you'll be brilliant. So Bill got hit by a bus. You got to bring somebody else on, code upgrade. What's the onboarding process at your company like? That? It is at our company. Actually, it's less that. What I should throw in there is a picture of somebody being thrown into the deep end of a pool. It's like, pff, enjoy. And a fire hose. Yeah, Chris back there joined on Monday, and the very first thing he got was, hey, we got this legacy MongoDB thing, fix it. For those of you who are not familiar with MongoDB, that's a very bad thing. So, you know, he had to deal with that. Stable storage. I know this sounds bad, but there's actually a point behind this. Those TPS reports, okay, the TPS reports are a bad thing. But document stuff, write stuff down. Write down the stupid stuff too. Processes, manuals, documentation can be, you know, with great power also comes great evil, or whatever. But it's not quite the quote, but whatever. But the point being, when Bill got hit by a bus and you got a new person in, do you have an onboarding process? I don't mean as in, this is the formal way we do onboarding. You got stuff for that person. Do they know where the code is? It's checked into GitHub. Really? Do we have passwords? Do we know what language he wrote this in? APL? Is there a course that we can go send the person to so they can learn APL? Whatever. Things like that. Have a mechanism by which people can be replaced. This sounds evil. And by the way, don't do this from a job security perspective. Do the exact opposite. Write your stuff in APL or Erlang. Seriously. Because with Erlang, the good thing is, if you write in Erlang and you get let go, not hit by a bus, then you're dead anyhow. But if you get let go, you can always find another job. That's easy. A good job, a well-paying job. But if you write in APL, they'll be banging on the door saying, please come work for us. Anyhow, that's a totally separate story. But the bottom line here is, document stuff, have mechanisms by which people can be replaced appropriately. And, you know, you'll be better off for it. If there's one thing I can leave you with for all of this, the question that you got to keep asking yourself over and over again in all of these is, you got to ask yourself, is it safe? Is my system fault tolerant? Is my organization reliable? Is my code fault tolerant? Is my code reliable? Is my system, repeat, just ask this over and over again, go through the cycle. Every time you ask yourself this, go through those checkpoints. Ask yourself, what are you doing vis-a-vis encapsulation? What are you doing vis-a-vis fault detection? If any of these, you can't answer these well, you have a problem. Which, to kind of make this very somewhat topical to what we're talking about, if you're writing your stuff in Erlang, I'm not saying this is going to happen magically, but you get a lot of this for free. It just kind of works that way. Yes, you still have to deal with system design and system architecture and service-oriented architecture, and you're still going to have the situation where your CFO runs off to Brazil, but you know, the Erlang's still going to help you there, but at least from a development perspective, you got some of these bases covered. And that's basically that. Any questions? Anybody? Questions? Yes?
Just out of curiosity, why do you hate MongoDB so much?
I don't necessarily...
Or what's the story behind it, I should say?
It's not as much that I hate MongoDB per se. For what it does, it is exceedingly good. It is designed as a mostly reliable data store. But if you want a reliable data store, it's not exactly what it is. I mean, I've written about this elsewhere, but For most of these things, you have to look at origin stories. What is the point behind something? And use it appropriate to its origin story. If you need to write fault-tolerant, reliable systems, use Erlang. Seriously, that's it. That's the origin story. If you want to write GUI stuff, don't use Erlang. Anything but. Use Node.js, use Backbone, use whatever, Ruby. Take your pick. Java, the origin story. I mean, there's a bunch of different things about this, but Java's origin story was, at the end of the day, garbage collection. It's the greatest thing in the world, garbage collection. Wow, party. So, stick to the origin story. From a data store perspective, Postgres origin story, it is a database designed by database developers. I mean, it's like, it works. It's like provably correct. MVCC, the works. MySQL is a data store designed by application developers. Everything that MySQL has was perfectly designed for building applications, the LAMP stack. It wasn't a LAP stack for that reason. MongoDB, my take on it, it's a database designed by GUI people. Spectacular documentation, brilliant usability. Horrible database, at least when it started. They're getting a lot better. Now they've got a ton of money. Hopefully they'll fix a lot of these things. But databases that occasionally lose data, or that you have to really work your butt off to make sure it doesn't lose data, and even then it does sometimes, that's not a database. That's a mostly reliable database. So you want to store your logging data where you don't mind losing some stuff? Fine, use it. I mentioned we use it. One of our our second most popular product line uses MongoDB as part of its standalone desktop controller. We sell about 100,000 of these things a month. It is brilliant. It's spectacular. Maybe less, maybe more, somewhere around 100,000. But the thing is, it's a desktop controller, and if there's a problem, you just remember the bit? Restart, poof, it just reinitializes, comes back up. You don't care if it's losing some data. It's not that big a deal. Hence, MongoDB. Any other questions? I believe we have lunch. Yes, we do. Garrett's already lunching.
I've learned to get there early.
Right.
So I'm hoping we have enough. But if we could, yeah. So it's lunchtime now.
That's my pleasure. Thank you very much.